Hello students, welcome to another session of All Force e-learning program. Right? In this session we shall study about a very important law, very vital thing in electrostatics called Gauss Law. Gauss Law. A very important law with respect to any entrance examination or it is for board exam or for any entrance. A very important law and a very important tool. It is actually a very important tool to deduce the relation for the electric field due to any charge. Any charge you can find out the electric field due to this, right? So before going to this one, let's have a review of what the things we have learned earlier. So charge, a fundamental property. Charging by, there are three methods of charging by friction, induction and conduction. Then force between two charges, Coulomb's law. Force F proportional to Q1 Q2 by d square. Then every charge interacts with the other charge by producing a field around it. The space where the effect of the charge can be experienced is electric field. So it produces lines of force around it, and with those lines of force it interacts with the other charges. Now this field, the space around the charge is spread by lines of force, and the count of these lines of force are given by the number of lines of force. Now this is measured as electric flux. So the electric flux is the measure of number of lines of force. Measure of number of lines of force passing through a particular space, whatever space area you consider. The number of lines of force passing through the surface is electric flux. And electric field is a space. Every field has got its own strength, intensity. The electric field intensity E, it is force per unit charge, F by Q. Then force due to point charge. We have deduced the formula for force due to point charge. 4 pi epsilon naught Q by R square. This is the formula for the electric field due to point charge. If there are many charges, then the resultant field is the vector sum of all the electric fields intensities. It is the vector sum of all the electric field intensities. E1 bar plus E2 bar dot En bar like this. Right? Principle of superposition, resultant electric field intensity. Right? Later we have talked about a dipole, the combination of two equal and opposite charges separated by a distance. Dipole. Then flux. So flux is the measure of number of lines of force phi. So it is equal to electric flux, the measure of number of lines of force passing through a particular space we consider. If the electric field is uniform electric field, if the field is uniform, in the sense the lines of force are parallel, uniform electric field, the type of field whose magnitude and direction remain same at all the points in the field. Uniform electric field means the lines of force are parallel like this, and the magnitude and direction of the electric field remain same at all the points. So in such case, if I consider certain area element A, the electric field is E, then the flux is E dot A. E, electric field intensity, it is also called as electric flux density. Electric flux density E, it is electric flux per unit area. The flux per unit area, the number of lines of force passing through per unit area is electric field intensity. So cross multiplying, I get flux is E dot A, or flux is equal to EA cos theta. This is the formula for it. Had it been a non-uniform electric field, in case of a non-uniform electric field, so the electric flux, the lines of force are non-uniform, a diverging field like this. Then imagine a small area element ds. A small area element ds whose normal, the direction is given by the normal like this ds bar. Then the small flux, the small measure of number of lines of force passing through the small, in non-uniform electric field, the small flux through the small area element, this is given by E dot ds bar. Or, so d phi is E ds cos theta. Then what is the total flux? For all the total flux through the total surface of enclosure, whatever we consider, the total flux is given by the integral of t phi. So this is integral E dot ds. So by the definition of electric flux in general, the definition of electric flux, it can be mathematically represented as, it is the surface integral of E dot ds. If I consider an enclosed surface like this, then over which if I imagine such area elements, the total electric flux through the total enclosed surface, it is given by the surface integral of the electric field over that enclosed area. So the surface integral of the electric field over that surface. So it is integral E dot ds. Integral E dot ds is equal to the total flux. Now, in this Gauss law topic, we are going to use this. So, to make you remember, I have just given you the review of all the things. Now, coming to Gauss law. Gauss law is an important tool, an essential tool, a vital thing which is used to measure the electric field. It is used to get the relation between electric field and the charge. Any amount of charge, any type of charge. You see, in Coulomb's law, Coulomb's law has a restriction. The limitation of the Coulomb's law is, it is applicable only to point size charges. Point charge, field produced due to point charge can be deduced from Coulomb's law. But if the same charge is distributed over a surface, we have taken in the earlier class, charge distributed over a line of charge, linear charge, a linear charge conductor like this, or a charged sheet. If a charge is spread over a sheet like this, plane, charge spread over a plane, continuous charges, right? For such a type of things, you cannot use Coulomb's law to find the electric field at any point there. In such cases, Gauss law will be of very simple use. It will be very useful to deduce a relation for the electric field due to any such charge. If the charge distribution is symmetric, it is very simple, right? It is even, Gauss law is also even useful to find out the charge distribution of the charge, how the charge is distributed over the surface of a conductor, right? Even to give the charge distribution also, this is helpful. The most important thing is, you can deduce the relation between the electric field and any charge of any shape using this Gauss law. A very important law. Let us understand. Now, what does the Gauss law state? Gauss has asked first he asks you to imagine a surface. An imaginary surface, you imagine an imaginary surface. It need not be a sphere or like that. It is based on the type of charge what you consider. Suppose if it is a charge, spherical charge, then imagine a symmetrical spherical surface over it. If it is a linear charge, then imagine a cylindrical surface, Gaussian surface over it. First imagine a Gaussian surface, an imaginary surface over which we are going to measure the flux. So if I imagine a Gaussian surface like this, right, then let us consider some charges exist inside this Gaussian surface. Q1, Q2, Q3, ... Some number of charges are existing inside the surface. Then, according to Gauss law, I was telling you in the previous session. Now, suppose if I imagine a surface like this and the charge is outside the surface. I was explaining a charge outside. Then, the lines of force produced by this charge pass through the surface this way, such that they enter into the surface at one end. They enter into the surface on one side and they leave the surface on the other side. The net flux is zero, right? This we have when the charge is outside. Now, on the contrary, what I am doing is, now I am imagining the charges inside the surface. Consider some charges inside the surface. And let me imagine a Gaussian surface. Gaussian surface can be of any shape. But it will be easy for us to deduce the things. While deriving the electric field, it is easy for us to deduce the electric field if you imagine a symmetrical Gaussian surface. But to measure the flux, you can imagine any type of surface there. So a Gaussian surface is imagined. Then Gauss law states that the net flux through this Gaussian surface the net flux emerging from the Gaussian surface, right? The total flux through the Gaussian surface phi is directly proportional to, it is purely directly proportional to the net charge that is present inside the Gaussian surface. The total charge that is present inside the Gaussian surface, Q inside the Gaussian surface. So, the total flux emerging from a Gaussian surface, the total flux through a Gaussian surface is directly proportional to the net charge that is enclosed inside the Gaussian surface. So, the flux is the measure of the total charge that is inside the surface. We are not bothered about the charge outside the surface. Flux here does not pertain to the charge outside the Gaussian surface. It is only directly proportional to the charge that is present inside the Gaussian surface. So when I remove the proportionality, so flux phi is Q inside by epsilon naught. While dealing with Coulomb's law, I have given you epsilon naught is the absolute electrical permittivity of free space. It's a permittivity of free space. Permittivity of free space or air vacuum. So I was telling you the value of epsilon naught is 8.854 into 10 power minus 12 Coulomb square per Newton meter square or Farad per meter. I have even guided you, instead of taking the value like this, better to take the value as 1 by 36 pi into 10 power 9 Farad per meter or Coulomb square per Newton meter square. This is the permittivity of free space, air vacuum free space it is, right? Epsilon naught. I have even given its dimensional formula, m minus 1 L minus 3 T power 4 I square, a very important formula which has appeared in one of the national entrance examination recently, right? A very important thing, so better remember this. So epsilon naught is absolute electrical permittivity of free space, and its value for air vacuum free space it is like this, epsilon naught. Instead of taking this, better take this for easy calculation, and its dimensional formula is like this. So according to Gauss law, the total number of lines of force, the measure of the number of lines of force, flux, the total flux passing through this Gaussian surface, it is purely directly proportional to the total net charge that is present inside the Gaussian surface. Now what do I mean net charge? Q inside net charge in sense, inside this Gaussian surface there may be positive charges or negative charges existing. So Q net charge net inside is, if it is a positive charge, take place, it is plus or minus Q1 plus or minus Q2 plus or minus Q3 dot plus or minus Qn. If it is a positive charge, take it plus. If it is negative charge, take it minus. Do the arithmetic and get the total net charge. So the flux passing through that Gaussian surface is always directly proportional to the total charge that is enclosed inside the Gaussian surface. Gaussian surface is an enclosed surface where some volume is enclosed inside, right? Volume enclosed. The enclosed surface, it has got no opening and no end, no start and no end ending there. It is enclosure. So the total flux through the enclosure is directly proportional to the net charge, right? Not individual, total net charge. Net charge is the sum of all the charges. Correspondingly, you should take the sign whether it is positive or negative. So this is the net charge. Then the total flux is directly proportional to the charge inside, and it is equal to Q inside by epsilon naught. This is Gauss law. Using this, you can measure the flux, right? If you can find out the total flux through the Gaussian surface, or when you know the flux there, you can even make out the charge that is present inside the surface there, right? So the total flux through the Gaussian surface, mind you again, the flux through the Gaussian surface is, it depends on, it is pertaining to, it is purely of the charge that is present inside the Gaussian surface. If there are charges outside the Gaussian surface, let us say Q1, Q2 and Q3 are outside, then the flux is nowhere concerned with these charges. Right? A very important point. Based on this, there are many questions asked. The flux through the Gaussian surface purely depends upon the charge that is present inside the Gaussian surface. So therefore, if we are not bothered about flux, never deals with the charge which is present outside the Gaussian surface. So, according to Gauss law, so the total flux through the Gaussian surface is the charge that is enclosed inside the Gaussian surface times 1 by epsilon naught. It is 1 by epsilon naught times the total net charge inside the enclosed inside the Gaussian surface. But we have already learnt, according to the definition of the flux, we have already defined it is the surface integral of, suppose there is a charge due to which I imagine a Gaussian surface. On the Gaussian surface, let the electric field be E, and I imagine a small area element at this over this ds. Then the small flux through that area element d phi is E dot ds. Then considering all such area elements over this Gaussian surface, the total flux, by the definition of the flux, we can write down flux is the surface integral of the electric field, integral of this electric field intensity of the charges on the Gaussian surface, right, over total Gaussian surface, enclosed Gaussian surface. So phi is integral E dot ds, right? It is the surface integral of the electric field over the enclosed Gaussian surface, integral E dot ds. Now putting that in this case, I get flux, which is the surface integral of E dot ds, is equal to q inside by epsilon naught. This is called the mathematical form of the Gauss law. It is the mathematical form, the mathematical or the differential equation of Gauss law, the mathematical form of Gauss law. So the integral E dot ds is equal to q inside by epsilon naught. This is the mathematical form of Gauss law. Now what does the terms in this equation represent? E represents the electric field intensity at any point on the Gaussian surface. It is the electric field intensity at any point on the Gaussian surface. The electric field strength, the resultant electric field strength on the Gaussian surface over the enclosed Gaussian surface. So the line surface integration of that, so integral ds over total surface area. Charge q represents the net charge that is present inside the Gaussian surface. It represents the net charge inside the Gaussian surface. So E represents the electric field intensity at any point on the Gaussian surface. I was telling you, usually while deducing the formula for the electric field intensity, we consider a symmetrical Gaussian surface. The Gaussian surface is symmetric with respect to the charges, so the electric field at all the points usually remains same. So this represents the electric field intensity at all the points on the Gaussian surface, and this represents the net charge that is present inside the Gaussian surface. So integral of E dot ds is equal to q inside by epsilon naught. This is the differential equation or the mathematical form of Gauss law. Gauss law can be stated like this. So the statement for Gauss law is the net flux, the total flux passing through an enclosed Gaussian surface is directly proportional to the net charge that is enclosed inside the Gaussian surface. So this is Gauss law. So mathematically it is flux phi is q inside by epsilon naught. Epsilon naught is electrical permittivity of free space. Now by definition of flux, we know flux is the surface integration of the electric field over the enclosed Gaussian surface. So E dot ds, surface integral of E dot ds. So equating both, I get integral E dot ds is equal to q inside by epsilon naught. So this represents, this is the mathematical form of Gauss law. mathematical form of Gauss law. A very important thing which is useful to measure. Using this law, we can deduce the electric field due to any charge distribution, and even we can find out the charge distribution. If you know the field, you can find the charge distribution of the charges there. Okay, thank you. Yes, let us now understand this, explain, let us understand the Gauss law in deep, right? Let us take the explanation for this Gauss law. Let me give you an example. With that, let us go clearly with respect to Gauss law. A very important tool, right? Very useful in deducing the electric field due to any charge distribution. Now, consider some charges. Let us say Q1. Here it is Q2. This is Q3. And somewhere here it is capital Q1. Somewhere here it is capital Q2. Like this. And the Gaussian surface, let us imagine a Gaussian surface like this. Then consider a point P on the Gaussian surface, right? So the net electric field at that point, is E bar. Net electric field at that point is equal to E bar. Now at this point, the electric field is produced by all the charges that are present in the vicinity of the point. The field here is produced by this charge, this as well as this, and even the field there is produced by even these charges also, Q1, Q2, these charges also. So the total field produced here due to all this, let the field produced by charge Q1 be E1 bar. The field produced by charge E2 be E2 bar, due to E3 be E3 bar, third charge, and field due to Q1, capital Q1, let us consider as E1 dash. Field due to Q2, capital Q2, it is E2 dash. So according to the principle of superposition, we know the net electric field at any point, the total resultant electric field at any point is the vector sum of all the electric fields that are produced at that point. It is the vector sum. So it is the vector sum of all the electric fields that are acting at that point, taking all of them simultaneously, right? So it is E1 bar plus E2 bar plus E3 bar plus E1 dash bar plus E2 dash bar. Some charges outside, field due to them also you have to consider. So the total electric field at this point is integral, it is total is given by principle of superposition. It is E1 bar plus E2 bar plus E3 bar plus E1 dash bar plus E2 dash bar. This is the net electric field at that point, right? Now here if I take a small area element, let me consider small area element, surface area ds. The small flux through that d phi, it is the net electric field intensity at that point dot ds. So therefore, the total flux passing, the small flux through that area element is d phi. It is E resultant dot ds. So according to Gauss law, the total flux passing through this, the net flux through this, according to the mathematical form of Gauss law, total flux is equal to the charge, total flux passing through it. By that we have taken it from the definition of the flux there. The net flux is the integral of E dot ds. E dot ds. So therefore, the total flux I can take it as integral of resultant, that is E1 bar dot plus E2 bar plus E3 bar plus E1 dash bar plus E2 dash bar dot ds. So flux phi is equal to, now taking it, E1 dash dot ds plus integral of E2 bar, E1 bar dot ds, E2 integral of E2 bar dot ds, integral of E3 bar dot ds plus integral of E1 dash bar dot ds plus integral of E2 dash bar dot ds. So the total flux phi is equal to, it is integral of E1 dash dot ds, E1 bar dot ds plus integral of E2 bar dash dot ds plus integral of E3 bar dot ds. Now coming to these two terms, the charges Q1 and Q2 are outside the Gaussian surface. I have explained you earlier, whenever the charge is outside the Gaussian surface, the flux due to that is always equal to 0. So whenever the charges are outside the Gaussian surface, the flux through the Gaussian surface is always 0. So this charge Q1 which is producing a field E1 bar, this is outside. So flux due to this and flux due to this is 0. So the total flux is equal to integral of E1 bar plus E2 bar, flux due to this, that is flux due to charge Q1, right? We know according to Gauss law, integral of E dot ds is Q1 by epsilon naught. Integral of E2 is Q2 by epsilon naught. Integral of this is Q3 by epsilon naught. The flux due to the charges which are outside is 0. So therefore net flux is equal to, it is Q1 plus Q2 plus Q3 by epsilon naught, net flux. But the total flux is due to the resultant. It is E1 bar plus E2 bar plus E3 bar. This is equation 1 and finally we got equation 2. Equating both. So integral of E1 bar plus E2 bar plus E3 bar plus E1 dash bar plus E2 dash bar dot ds is equal to Q1 plus Q2 plus Q3 by epsilon naught. This is to be understood. This is the actual meaning of Gauss law. In this actual meaning of Gauss law there, in this equation of, in the mathematical equation of Gauss law, I have written E dot ds. The surface integral of E dot ds is Q inside by epsilon naught. I mean E, the E term in this one represents the electric field due to all the charges that are present in the vicinity of that point P, where you are finding the electric field. E represents the resultant electric field due to all the charges present in the vicinity, whether they are pertaining to Gaussian surface or not, we are not bothered. It is a field due to all the charges. But Q here, in this term Q is pertaining to only those charges which are present inside the Gaussian surface. It is always concerned about the charges that are present inside the Gaussian surface. We do not consider the charges which are present outside the Gaussian surface. So integral of total electric field due to all the charges dot ds is the total net charge that is present inside the Gaussian surface by epsilon naught. So to understand Gauss law is explained clearly by an example like this. So what I have considered is, I have taken some charges inside the Gaussian. This is a Gaussian surface, some Gaussian surface. 3 charges inside and 2 charges outside. Now I have to calculate the electric field at this point. Gauss law actually is helpful to determine the electric field due to any charges, any charge distribution, right? So using this formula, integral E dot ds Q inside by this thing. So I want to find the resultant electric field. The resultant electric field due to all these things, let it be E resultant E, right? Consider a small area element ds, right? At this point, the small flux, at this point the total, all the resultant electric field, we know the resultant electric field due to all the charges is the vector sum according to the principle of superposition. It is the vector sum of all the electric fields. So therefore small flux through this area element, if the resultant electric field intensity is ER, then it is ER dot ds. So therefore the total flux is the integral of ER dot ds. The total flux through the Gaussian surface is the net electric field ER dot ds. But the net electric field is due to all the charges. So the electric field is due to E1 bar plus E2 bar plus E3 bar. Q1 will produce E1, Q2 will produce E2, Q3 will produce E3. Q1, capital Q1 charge outside the Gauss circle will produce a field E1 bar dash, E1 dash bar. The Q2 charge which is outside, capital Q2, this is producing a field E2 dash bar. So field due to all the charges, all the fields, the vector sum. This is the vector sum of all the fields. Dot ds. Do some mathematics. I multiply ds. Right? We know integral E dot ds. Right? Even integral E1 dot ds is the flux through due to the charge Q1. It is a flux due to charge Q1. So therefore it's Q1. This is due to Q2. This is due to Q3. But capital Q1, capital Q2 here, they are outside the Gaussian surface. Flux due to them is 0. So therefore the total flux, it is integral E1 dot ds, E2 dot ds, E3 dot ds 0. But the total flux is nothing but, according to Gauss law, it is Q1 by epsilon naught. So due to first charge Q1 by epsilon naught, second charge Q2 by epsilon naught, third one Q3 by epsilon naught. Adding all, it is like this. So from equation 1 and 2, I write the explanation, I write the Gauss law. The final statement for Gauss law is integral of the electric field is due to all the charges that are present in the vicinity of the charges, vicinity of the point there. So it is E1 bar plus E2 bar plus E3 bar, E1 dash bar, E2 dash bar. Dot ds. But the charge, net charge is only due to the charges that are present inside the Gaussian surface. Q1 plus Q2 plus Q3 by epsilon naught. Right? So integral E resultant dot ds is Q inside, net charge inside by epsilon naught. This is the final statement of Gausslaw. Right? Thank you.